It's our pleasure to share with you this tutorial on thermal designs using vapor chambers for smartphones, laptop, high-performance computer, and power electronics. So I will give the first session. It's about 45 minutes. And then Dr. Ryan Lewis, he will give another section after my presentation. So what I plan to do, I will give you a quick introduction about vapor chamber, and in particular thermal ground plane, because thermal ground plane is our company product. So we know this very well. Also, I don't want to talk too much about other companies' product because they may not be happy about my sharing about our knowledge on their vapor chamber. So the main topic will be thermal ground plane. But we're talking about vapor chambers. They are, one way or another, they are similar, okay? Then I will talk about one important mechanism. It's called vapor transport dominated TGP, okay? And I will explain, a lot of system designers, they use thermal conductivity. But you're gonna find out using thermal conductivity in your system design is not a right way to do it, right? So I will explain that to you. I will explain what is the physics involved in this, okay? Then I will talk about thermal systems with a TGP inside. And I will tell you sometimes you don't want to look for high performance TGP. Sometimes reasonable performance of TGP is good enough, okay? But you will gain something else. So I will give you one example using a laptop with a TGP inside. And then I will also talk about thermal systems with a high power TGP. So Ryan demonstrated we can remove 700 watt from 1 inch square. So I will talk about this high power TGP. Then I will talk about what's the advantage, how we can look at this kind of TGP from a system design point of view. Okay, and that will be at the end of my session. And then Dr. Ryan Lewis will talk about another exciting TGP developed. It's called foldable TGP. In particular, with the foldable TGP, Ryan will show you two major applications, how they can benefit from foldable TGP. In particular, he will introduce some details about thermal systems, how we develop simulation model, how we model a system without TGP, with TGP, and also what we can do. And during this presentation, he will introduce one very important concept. As I mentioned, we should not use thermal conductivity. And naturally, you will say, well, all right, then what do we do? Well, Ryan will tell you a scalable thermal ground plane model, that's kind of vapor chamber model. You can use that model. That's much more scalable than just effective thermal conductivity. So that's why you will learn that detail. That detail will be very important in all the future thermal system design if you want to use vapor chamber, okay? I'm pretty old. When I was young, I entered this thermal management community in 1984. In 1984, there was a break news happened 2 years ago. In 1982, IBM developed this, it's called thermal conduction module. Okay, thermal conduction module. I've been working on thermal management for, I don't know, so many years. But it's very clear, thermal conduction, heat conduction, is the most important cooling technology, okay, or heat transfer mechanism, okay? So heat transfer from device to package, eventually go to air. But this conduction, or we call heat spreading, is the number one mechanism, number one design consideration. We have to be very careful, okay? So IBM named this module as a thermal conduction module. Because of this module, our entire packaging community, our level move one level up. Okay, so nowadays packaging is so well known and so many people working on packaging. We have to recognize the important contribution of thermal conduction module in 1982. But this module also tells us heat spreading, okay, using conduction is essential in every system, all right? And of course, since 1982, there have been a lot of new materials developed. Not only new materials, also heat pipe was introduced. And today, vapor chamber become a common element, components you can use. Okay, so vapor chambers are good for a wide spectrum of applications, and that's the purpose of this tutorial. So we will share with you what's happening today, also what's going to happen in vapor chamber technology 2 years from now, 5 years from now. So you will see a spectrum of different vapor chambers to be developed. Also, you will learn, okay, how can you use them as a thermal designer? So that's the purpose of this tutorial. So here I give you a very quick overview. You know, it's not comprehensive. I just pick up some application I know about. A Microsoft Surface Book introduced in November 2015. They use a piece of vapor chamber, okay? Oh, by the way, this is a vapor chamber. Vapor chamber basically is a heat pipe, okay? So heat going into this enclosure, and then there's a water inside, so there's evaporation. So this evaporation absorbs heat. Then water vapor transfer heat from hot to cold, and there's a condensation, and then become liquid water. And liquid water is poured back through this weakened structure. So that's complete we call heat pipe operation. So vapor chamber is nothing but two-dimensional heat pipe. Okay, I mean, that's the major difference, the two-dimensional. Because it's a two-dimensional, it's a much better than heat pipe for spreading. Your heat spreading is two-dimensional nature. In fact, sometimes we need a three-dimensional. All right. So that's why Microsoft introduced this in laptop. And then Huawei introduced this flat heat pipe to their smartphone in October 2018. And Razer was another pioneer using this for their gaming phone in November 2018. And then August 2019, Samsung introduced the use of vapor chamber. And since then, vapor chamber become very popular in high quality smartphone and also laptop. Okay, roughly speaking, last year, 2020, they reported about 60 million vapor chamber used in smartphone. And this year, they expect to see about 100 million. So roughly speaking, 20% of 5G smartphone, they are using vapor chamber. Okay, and this kind of vapor chamber, it's not expensive. It costs about $1. So it's not expensive. So that's why we expect to see a wide spectrum of applications using vapor. Right, and the number we expect to see 200 million, 500 million, eventually go to billion. Yeah, okay. I'm going to use our own vapor chamber as an example. So this is our vapor chamber. We call this thermal ground plane, TGP, because this was developed when we were funded by DARPA. I was a PI as a professor at the University of Colorado Boulder. At that time, DARPA called the program as a TGP program. And Tom Kenny was the first program manager, and then late Harvey Barcohen was our program manager. So we do miss Harvey. He was very important in TGP program. Okay. At the end of TGP program, Harvey was pushing us, say, hey, everybody try to find application. So gradually we improved technology substantially, and we identified a new application. All right. So this is our structure. So what's the difference between our TGP and traditional vapor chamber? We use flexible circuit board. Okay, so flexible printed circuit board is the main material used to fabricate our thermal ground plane or our vapor chamber. Okay, So you cannot see those liquid pillar. They are very small, but you can see cross section. We have a liquid pillar. Okay, so we can order flexible circuit board with liquid pillar etched. So that's pretty easy. Then we bound copper mesh. So this is a copper mesh bounded onto liquid pillar. So that becomes weakened structure. Then on another side, we have vapor pillar. Vapor pillar are big. They are big and spacing is large, and also it's very tall. So vapor can transfer this, and you can see those pillars. And then the two pieces, they are hermetically sealed, and we apply vacuum, then we charge this with water, and that's it. That become a vapor chamber, right? So because we are using flexible circuit board, because everything we do is low temperature, that's why our thermal ground plane can be flexible. Typical vapor chamber, you are not allowed to bend vapor chamber because their copper is soft, because their sintering temperature or brazing temperature, diffusion bonding temperature is much higher, 650 degrees C or 800 degrees C. So they have a crystal much bigger and soft. Yeah, okay. Anyway, that's kind of different approach. So first, I want to introduce you how good is vapor chamber. So here's a good comparison. This is a 10-layer graphite heat spreader, okay, from one of the leading supplier in graphite. So it's very thick, 490 micron. End up with 550 because we grew another Kapton film for infrared image. Okay. On the right-hand side is our vapor chamber. It's a 310 micron. Again, we grew another 50 micron Kapton film for infrared image. Okay. This graphite is a very high quality graphite. Thermal conductivity is over 1100 watt per meter per Kelvin. Typically for such a thick graphite, 490 micron, thermal conductivity is lower, 900 or 700. So this is really state-of-the-art, high-quality graphite. So we'll compare these two. Okay. And you can see this infrared image, and this one, the power, it's about 5 watt. So we have a 5 watt from top, and you can see 10-layer graphite. The temperature gradient, temperature difference is about 9 degrees C. With the same power, TGP temperature difference is about 2.4 degrees C. All right. So this is like 9 degrees C versus 2.4. Most of customers, they use graphite or they use TGP. This temperature difference across this heat spreader is their number one concern. Okay. As you can see, TGP is about 3 times better than graphite. And keep that number in mind. That's a good number to remember. All right. But you are going to find out this number may vary when the temperature changes. All right. So overall, the effective thermal conductivity of TGP is much, much higher than graphite. And this graphite is much, much higher than typical graphite or much higher than copper. All right. So that's why you can see nowadays gradually, graphite is used everywhere, heat spreader. But gradually, thermal designer, they replace graphite by vapor chamber one step at a time. And this is happening now. Our TGP have been successfully commercialized. One of our licensee is Forcecon. It's one of the leading company in fan, cooling fan for laptop. So they license our technology. So they mass produce our TGP in December 2020. And they are in the process to reach 2 million TGPs per month. All right. A good example of the TGP they produce, one is 110 millimeter, 130 millimeter times 0.35 millimeter. Okay, that's good. Another one is 0.25 millimeter with a smaller size. So that's kind of notable examples in TGP commercialized. Okay, it's being used in smartphone and the laptop. Okay. Also, our company, we're in the process to introduce our own product. And this is another exciting TGP. And you can see the thickness is only 0.225 millimeters, so 225 micron. very, very thin. And Ryan compared this one with copper. So this is a 250 micron copper. You can see the temperature difference is huge in copper reference sample. That's a 33 degrees C. And then TGP is a 2.2. So usually we use delta T to estimate what is the thermal conductivity. The customer always want to know, hey, YC, what's the thermal conductivity? Even though I'm going to tell you thermal conductivity is not the right number to design. But for most people, this is the number to get started. All right, so we have to tell them something. So we use delta T as a reference because copper is 400, so the ratio is 15. So we say, all right, our TGP thermal conductivity is about 6,000. All right, okay. So this happened at 7 watt natural convection. So that's one. Delta T, very important, effective thermal conductivity. Now, another thing you need to consider is what is the maximum power? Okay, so that means how much heat I can spread inside this TGP if my external cooling is not a limiting factor. You see, this maximum power is usually determined by many factors, but we want to know what is the intrinsic maximum power. So that's why you will see a lot of vapor chamber companies, they will tell you, okay, my maximum power is 5 watt, 7 watt, or 11 watt. In this case, this one is 11 watt. And 11 watt is pretty powerful. But usually we say 11 watt in a forced convection condition. Because at 11 watt in natural convection, this TG temperature will go over 100 degrees C. That's bad. So that's why we have to apply fan to cool this in order to identify intrinsic maximum power. All right. So we will talk about those numbers again. And then the best one demonstrated in the vapor chamber community was done by Ryan almost 3 years ago. He demonstrated 0.15 millimeter vapor chamber. So that's why as a thermal designer, I want you to see as a potential roadmap, better and thinner, more powerful vapor chamber is coming out. All right, so no problem. Vapor chamber community, we are very competitive. We are going to introduce a better and better product to serve your thermal system. Okay, this one is only 150 micron, and you can see the delta T is only 4 degrees C, and the graphite, that's 28 degrees C. Okay, the heater is larger, so it's 1 centimeter by 5 centimeter. All right, so it's the one-dimensional, so we can compare. As a result, the effective thermal conductivity is about 6,300. All right, at the 7 watt. All right, in this case, maximum power is 15 watt. All right, okay. So that's why there are a lot of good stuff in the vapor chamber community. You expect to see a lot of vapor chamber to be available, and you can use it as a thermal designer. 0.3 millimeter is kind of standard of vapor chamber used in smartphone, and getting thinner, 0.25, 0.2, 0.15. We believe we can go all the way down to 0.1. Okay. Not only form factor, also cost, because vapor chamber in the major market is a smartphone, so cost has to be extremely competitive. So we're talking about dollars, $1, $2, okay, and $3. So it's not very expensive. All right. So that's why. We're not talking about something very expensive. That's why we expect to see a wide spectrum of applications because the vapor chamber is ready to serve. It's driven by smartphone, by laptop, but you can apply this to many other applications. Okay. So that's a quick overview of vapor chamber using our TGP as an example. The next, I will talk about one important design consideration, and that's something you have to understand. You have to understand why this vapor chamber or TGP, you cannot treat them as a heat pipe anymore. All right, okay. So that's what we call vapor transport dominated TGP. I gave 2 thermal conductivities so far. But I will tell you in the future, don't ever use thermal conductivity. But anyway, we'll see. Okay, so we have to use it, but meanwhile, I tell you, don't use it. Okay. So Ryan did a calculation and a measurement. He tried to understand thermal resistance. So there's the heat source, and there's a thermal resistance across the cladding, that's the casing. There's another thermal resistance across mesh with water. Then there's a thermal resistance corresponding to vapor transport. Okay, water vapor transport. And go back, resistance across mesh and water, resistance across cladding to heat sink. So when he calculate this contribution from each thermal resistance element, he found out the vapor transport thermal resistance was nothing when the TGP was 1 millimeter. Okay, 1 millimeter. In our DARPA TGP program, our goal was to demonstrate 1 millimeter TGP. At that time, 1 millimeter TGP in 2008 was ultra thin vapor chamber. Okay, but 1 millimeter, no problem. Vapor transport is nothing. Then we improve our technology. You can see we demonstrate 0.25 millimeter TGP. And you can see the contribution of vapor in total thermal resistance is very different. Now the total thermal resistance is dominated by water vapor. So this water vapor transport become the barrier, the major thermal barrier. Okay, I hope you can understand this big difference. That's why traditionally when people design heat pipe, when people design vapor chamber, because they are thicker than higher than 1 millimeter, they say don't worry about vapor transport. The longer, the better. Okay. However, when we design thermal ground plane with a thinner structure like a 0.25 millimeter, the longer doesn't mean it's okay. Okay, because you have a larger pressure drop, you have a higher thermal resistance corresponding to vapor transport. So that's a paradigm shift. And you may say, how about thicker vapor chambers? I don't need to worry about this. Well, you do need to worry about this. When your power goes up, like 700 watts, you have so much pressure, heat flow, mass flux going on, and you need to consider vapor transport. Okay, so this is something new in this new application. All right, so that's something I want to share with you, so you gain a little bit insight, and also when Ryan talk, you will understand the model, scalable model Ryan is going to introduce. That will be very powerful in your thermal design. Okay, don't ever use thermal conductivity in your thermal design. Okay, if you are a serious designer. So what is this vapor core transport? Okay, so we studied this vapor transport in two parallel plates. Okay, so it's a porosity flow. Okay, so we study vapor transport from, for example, high temperature to low temperature. So we can calculate pressure drop. Then from the pressure drop, because this is a water vapor, there's a Clausius-Clapeyron relationship. So this is thermodynamics. So saturation pressure and saturation temperature, there's a relationship. Okay, so there's a relationship. So from the pressure drop, okay, we can derive temperature drop. You know, they are related. So pressure drop, we can derive temperature drop. So in this case, temperature drop is 30 degrees C from 70 to 40. Then I can derive what is the pressure drop. Okay, so if I have a different pressure drop, I will have a different temperature drop. All right. So using this thermodynamics, we can calculate delta T from the delta P. Then based on delta T and heat flows, we can calculate thermal resistance. Then from the thermal resistance, using one-dimensional heat conduction, we can derive the effective thermal conductivity. So effective thermal conductivity and the thickness and the width, and this is the length, and this thickness and width, that's a cross-sectional area, I can calculate effective thermal conductivity. All right. So that's why even though it's a vapor transport, and you say, well, how did you convert vapor transport convection into thermal conductivity? Because we convert thermal resistance into effective thermal conductivity. That's why we can derive this. Right? So that's why we always call this effective thermal conductivity rather than thermal conductivity. Also, you understand this is not a material property. Okay, this is a fluid flow phenomenon. You can see this effective thermal conductivity is a function of density. Okay, it's a function of density, all right, and with a square, all right. So it's a highly dependent on density. And pay attention to this water density. And Ryan prepared a table, and you can see this water vapor density. It's a highly dependent on vapor temperature. You see, changing from 20 degrees C vapor to 90 degrees C vapor, the vapor density increased from about 0.025 to about 0.4. So almost 10 times increase. So huge, right? Huge. That's why the one thing that's very important is when we estimate effective thermal conductivity of vapor transport, we found out we have to use log scale because effective thermal conductivity changed so much when the temperature changed a little bit. So with a 100 micron vapor core, if I change from 30 degrees C water vapor to 50 degrees C water vapor, you can see the effective thermal conductivity of water vapor transport changing from 2,000 to 10,000. Okay, so it's a huge change. It's a huge change. All right, so that's number one. Also, number two, when the gap is changed, when I reduce the gap from 100 micron at 45 degrees C, okay, reduced from 100 micron to 50 micron, and I change effective thermal conductivity of vapor transport from 8,000 to about 2,000. So you see there's a major change with a 50 micron change. If I increase to 200 micron, effective thermal conductivity increase from 8,000 to almost 40,000. Okay, so it's huge change. That's why this vapor transport is highly dependent on temperature, also highly dependent on the gap. All right. So that's why in thermal design, you have to understand because of this mechanism, this so-called effective thermal conductivity does vary, even with the same TGP. So here is one example. We call this as a heat pipe operation. So heat coming from hot and go through TGP transfer to cold. All right, 6 watt and go to 45 degrees C. You can see this is a simulation. All right, we can simulate this. And then another approach. So this is what we call heat pipe from hot to cold. Another one is more like a smartphone or laptop application. So I have a heat source, but then the cooling is done by distributed cooling. Okay, cooling happens everywhere. Okay, so it's a distributed cooling. Corresponding to distributed cooling, again, you can see temperature difference is quite different. Okay, it's quite different. So that's why you found out even with the same TGP, but this heat transfer is quite different. Okay, all right. And that's the story I want to share with you. With a heat pipe operation, delta T is about 12 degrees C, and I can calculate effective thermal conductivity is about 3,000, not bad. However, with a distributed cooling, effective thermal conductivity is much higher, 5,000. All right, so it's much better. And what's the reason? If you pay attention to the temperature gradient, you found out this temperature change from hot to cold is ranging from about 64 to 65, so near isothermal. Also, temperature is high, 65, 64 degrees C. high temperature. So what is the water vapor density? Water vapor density at 64 degrees C is very, very high. Very, very high. Okay? So water vapor density is high, effective thermal conductivity is very high. Okay? And with this heat pipe operation, you can see the temperature changing from 50 degrees C down to 46 degrees C. Large temperature difference in the colder region, temperature is lower, like 46 degrees C. So the temperature is lower, density is lower, effective thermal conductivity is lower. All right, okay. So that's the physics involved. And that's why we have one conclusion. With the same TGP, we may end up with different effective thermal conductivity. Okay, that's why I say don't use a single number in your thermal design. And then Ryan simulates something that's much more complicated. So one is from heater and distributed cooling. It's very good. The LRT is very low. All right. Maximum power, 13.5 watt. All right. But then if he has another heat input, heat output from a particular region, and suddenly delta T increased from 1.3 to 2.2, and also worse, maximum power reduced from 13.5 watt to 7.6 watt. Okay, that's why this gives you an idea. Heating, cooling configuration is very important. Keep in mind, it's the same TGP. Okay. Also, if you change cooling condition, you end up with different numbers. All right. So that's why the take-home message we want to share with you is don't ever use single number as a thermal conductivity. Then you say, okay, I cannot use thermal conductivity. What can I do? Well, you have to wait. Ryan is going to tell you. Okay, Ryan is going to tell you he got a great solution to help you. And I hope that will be the major contribution from this tutorial. And I hope you will be excellent thermal designer. So another interesting thing, a lot of people got confused, is what is the maximum power? Okay, maximum power, Qmax. As I mentioned, Qmax is an intrinsic property of TGP. So what is a Qmax? At maximum power, you can see this white bar, that means dry out happens. So that means when we did experiment, we say, okay, this is the maximum power, 13.5. Don't go higher because this will burn off. So when at this power, the capillary pumping pressure, you see there's an evaporation. So this capillary pumping pressure is served like a vacuum. So this pumping pressure will pull liquid water back to this hot region. So this pumping pressure is corresponding to the porous medium, this size, porous size. This pressure will drive vapor transport, also will pull liquid water back. So you have a high pumping pressure, but when the pressure drop of vapor transport and also pressure drop of liquid flow, when these two, you add them together, plus gravity. If your heat is happen at top, you have a plus gravity. When they are balanced, that's the maximum power. Okay, and that's how you can see this 3 pressure drop plus gravity. You can see 5 watt, no problem, 10 watt, 12 watt, no problem. 13.5, well, you hit the capillary pumping pressure. That's the maximum. You cannot go higher. When you go higher, there will be burn off. So that's what we call Qmax. Okay. Qmax. Then I ask you a question. The smaller the TGP, the higher the Qmax, or the lower the Qmax. Okay? In fact, from here, you can see I reduced size by half. My Qmax increased by 2 times. Okay, so 25 watt rather than 13.5. All right. So smaller TGP, Qmax is higher. So sometimes it goes against our intuition. We usually cooling, we say larger area, maximum power is higher. But keep in mind, Qmax is intrinsic. That means the pumping pressure, pressure drop resistance, that balance. That's why smaller means I can drive more power throughout this vapor chamber. Okay, so that's something, that's number a lot of thermal designer got confused. Okay, all right, so that's the thermal conductivity. So Ryan is going to tell you this thermal conductivity is very strongly dependent on the configuration, heating, and cooling conditions. All right, so don't use this in a serious thermal design. But what can we do? Well, Ryan will give you a scalable TGP model in his example. He will talk about some details. Right. So next, I will give you another application, thermal systems with a TGP inside. Okay, so this is another TGP developed. It's a 25 centimeter by 15 centimeter by 0.55 millimeter. Okay, and you can see this power. Okay, 50 watts. Okay, we can remove with this size. So effective thermal conductivity is 17,000. Again, I give you this number because I have to give you something so you can appreciate. But this number is dependent on heater and the cooling. Okay. And then we put this into a laptop. Okay, into a laptop, and you can see we put a decover, and we study upright condition and tip back condition, and we try to compare. And you can see with a TGP, temperature distribution is much more uniform. That's good. And that's what we want. Okay. And we found out with a TGP inside, we can stop the cooling fan. So no fan is needed. We can remove the heat. We also use experimental data to calibrate our model. Ryan is going to talk about this. Okay. Once calibration, you found on the model, the experiment match very well. All right. And then once we have a model, I model this TGP we developed. All right. Effective thermal conductivity is pretty good, 16,000. Then I say, okay, I reduce this. So why do I want to reduce this? Because I can reduce the thickness of the TGP. I reduce from 0.55 to 0.35 or to 0.3. So because my vapor transport pressure drop is higher, my effective thermal conductivity dropped. But with a drop, but then you found out the difference is nothing. Okay? So my maximum CPU power is reduced from 13.4 to 30.2. So it's not a big deal. All right? So sometimes this kind of thermal design is very important because only 0.2 watt difference, I can reduce vapor chamber TGP from 0.55 to 0.35. So what do I gain? With a thinner TGP, it's lighter. So it's only 32 grams. Okay? Traditional, if we use 0.55, we need about 45 grams. And sometimes all copper approach, that'll be 90 grams. So huge difference. Okay. So with this kind of a trade-off study, our TGP can be even lighter and then graphite or laminate. Okay, so that's the trade-off I want to share with you. Also, I want to share with you another potentially exciting TGP to be introduced. That's called all polymer TGP. Everything is polymer, no more copper, so no millimeter wave attenuation. So this will be excellent TGP for 5G application because it's RF transparent. We already demonstrate feasibility. This should be introduced maybe 2 years from now. So you will have this kind of all polymer TGP available. Okay. So another one is called foldable TGP. All right. So it's a folding. And so Ryan's section, he will talk about this. And so he will also talk about how to use this in novel system. Okay. So finally, I will talk about another application. That's a thermal system with a high power TGP. Okay. So Ryan demonstrates high power application. All right. So this is a high power TGP. If the heater size is 10 millimeter by 10 millimeter, he demonstrated he could remove all the way up to 475 watt. Okay, huge from 1 centimeter by 1 centimeter. All right. And then if he increased the heater size, because people told me with this kind of power, nobody will use 1 centimeter square chip. They say nobody will do that. They will use multi-chip module, all right? So with a multi-chip module is much bigger, 25 millimeter by 25 millimeter, and Ryan demonstrated all the way up to 800 watt. But I think with a reasonable superheat, 15 degrees C, it's about 700 watt, okay? So this delta T including TRM. So that's why I hope you can appreciate vapor chamber is indeed very scalable. You know, I was talking about 2 watt, 5 watt for smartphone, but we can make it thicker, and then suddenly this become high power. Of course, thickness become 4 millimeter because it's a vapor transport, right? So it's very important. Of course, he did a measurement. We monitored the temperature on the TGP. We found out it's almost isothermal. So heat flux spreading is very effective from the heat source to entire TGP. So this heat flux reduction is substantial. It's almost isothermal case, all right? And that's very important because this heat has to be removed by cold plate. And that's something I want to share with you. And this cold plate doesn't need to be fancy because the heat flux is effectively reduced. So the heat flux level transferred to cold plate is so low, we can use a very simple cold plate for cooling. All right. So that's why you can see some measurement, and Ryan measured the temperature of a heater, temperature of TGP, and also temperature of cold plate. All right. Okay. Then he can also measure delta T, and using this, he reported the result. Okay. And also there's a clamp where we use thermal grease as a TIM in this case. And we can apply 100 PSI. If people always ask me, hey, what's the maximum pressure? You see 100 PSI, no problem. Okay, no problem. Right. So that can be done. What's the beauty? We use a very simple cold plate to complete this entire system. All right. You can see the effective heat transfer coefficient convection is only 3,500. So this is just simple one pass heat exchanger. So very simple. And that's the key because we study another application using a very famous paper published in JEP. Okay, this is for IGBT, and they use this copper aluminum nitride and also very novel aluminum silicon carbide heat sink. This is one of the best approach for power devices. We study the same device. We say, okay, instead of this good material, let's try to use cheap TGP to see what we can do. And you found out, number one, junction temperature reduced. But that's not a big deal. The big deal is what? And because the heat spreading is good, but it's not good enough. So heat spreading is not that good. So they had to use impinging jet. But with TGP, heat spreading is so good, and you need only simple liquid cooling. That's why from system point of view, sometimes, everybody's doing this kilowatt. Everybody can do kilowatt. But you have to look the whole thing from system point of view, okay? And the way I see using TGP in a vapor chamber, the best outcome is I simplify my liquid cooling. Okay, that's the major contribution, okay? So very quickly, I give you a review of thermal ground plane. I talk about vapor transport dominated TGP, and I give you many warnings. Don't ever use thermal conductivity in your thermal design, okay? Because they do change, even with the same TGP, all right? I also share with you, sometimes you don't want to go for high performance TGP because you can reduce weight, you can reduce cost, you can do many other things with a lower performance TGP if you have a good thermal design. Also, I share with you a good number, 700 watts, no problem. We can do this nowadays, all right? So that will conclude my section.